I work in model theory, and I want to speak about some connections I see between Grothendieck's work and what has happened in the past in model theory and what is happening now in model theory. So it will be kind of very tentative. It is very much a work in progress. I'm not officially a historian of mathematics. I'm very interested in issues connected to history of mathematics, and we will see a little bit of that here. But let us begin by listening to the man himself, Grothendieck, in L'Aventure Solitaire, the solitary adventure. What interests me in this past is not at all what I have done, whatever its fortune is or will be, but rather what has not been done in the vast program that I had then in front of my eyes, and of which just a little part has been realized by my efforts and that of friends and students who sometimes wanted or accepted to join me. Without having looked for this or foreseen this, the program itself has renewed itself at the same time as my vision and my approach of, and this is a wonderful word, the chose mathématique, the mathematical thing. That's something, an undefined, that is very beautiful. Then he goes on, and then les mystères qui m'ont le plus fasciné, tel celui des motifs. So we heard John Baez, for instance, speaking about that mystère, or that of the geometric description, of the Galois group of Q bar over Q. So in a way, all of this kind of encapsulates what the little thing that I want to share with you today. So it is this unknown. Many things were also unknown to him. He speaks about them here, and in a way have been or are being now realized. So our stops today. First of all, there will be a descent. Galois theory of model theory will be a kind of a descent, and I will try to describe a little bit how it is done. So if you're a specialist in Galois theory, bear with me. My description will be necessarily extremely rough and extremely incomplete, but I want to single out one point that is important. Then the middle of the talk is about stability. And stability is a central concept in model theory. It gives the name to the advanced part of model theory. It is called stability theory or classification theory. I will describe a little bit why that's important in model theory and why I see a link with Grothendieck. Well, it is not just I that sees a link to Grothendieck. Some of my colleagues have singled out that indeed stability itself is a Grothendieck'ian concept. It was discovered or invented by Grothendieck in 1952. Some of you here really know the literature, really know what was happening in his writings in the early 1950s. It has been spoken about by Carmen, for instance, or by someone else. And that already has a first definition. Of course, it was not called that way, and it was not used that way, and it was only for one specific category, and it was then later expanded. So we will first see the expansion, and then how, in a way, there is the germ of the idea in Grothendieck. So, and then I will speak kind of more roughly of three ascents. So Rzyszowski's core, that's from a very recent work of Rzyszowski. Beyond first order, that's part of my own work with Scheller and with my students in Bogota and some other colleagues. And higher stability, new kind of line that has been opening and it is now, as I speak, blossoming here also in Los Angeles at UCLA. A colleague of mine, I will mention a little bit what is happening, and it is some kind of parallel to higher stability, to higher category theory. So first of all, our descent. First of all, a disclaimer: when you speak about Grothendieck logic, you could also speak about topoi and sheaf semantics, but this I won't do today. So today it's really about Galois model theory, and the bonus I can claim before, the role of stability and his role, Grothendieck's role in coining out that concept. Anyway, so we have this picture here for multi-theoretic Galois theory. So I put here some important names, of course, Galois. There is Scheller at the background of this possibility. Poisat in France was the one who fleshed out the possibility of making explicit the Galois theory. But I use here a very nice explanation, much recent by Medvedev, Alice Medvedev, and Villaveces from number theory, and she's a null theorist. So you have an ascent and the descent. You have on the left-hand side fields going up from K to F, and then up to the algebraic closure of F. And then you have some intermediate extensions of F. So fields are, you look at extensions of fields on the left-hand side. And in the right-hand side, you have the automorphism groups of the big field over the small one. So this here will be one group, larger group, until you go all the way to F over K. And then you have this correspondence going up and down and going this gives you two adjoint functors. And this is what, this is a very important part of the description of Galois theory in the classical case. So why model theory? Now, let us step back to 1980 for a second. Scheller defined something he called imaginaries in model theory. So you take an arbitrary first order theory, T, and if you want to have quotients in the class, normally those are not the final objects, but you might be interested in having quotients. And he did this for purely stability theoretical purposes. It kind of smooths out the theory, it kind of gives better invariants that he was interested in at the time when he was trying to classify. There will be a little bit of this later. So one major kind of technical step was adding definable functions as elements, as new elements he called imaginaries, and expanding your models with imaginaries. And then asking if the theory has elimination or doesn't have elimination of imaginaries, that was yet another step. So this technical looking device of expanding the theory was recognized by Galois-theoretic very early on in '83. He notes that Schellach's imaginaries are exactly what's needed for a general Galois theory for models of T. So note Galois theory for algebraic geometry or for fields or for arbitrary models. You can also do a Galois theory. Yet arbitrary is not, that's what we want, and then we'll see what restriction there will be. But at the beginning, it works quite well. This paper in French in the Journal of Symbolic Logic, in Théorie de Galois Imaginaire, is a seminal paper of this line. He fleshes out what happens here, and he says the model theoretic proof of Galois of Galois's correspondence is much closer when you do it model theoretically to the indications of the proof that we have in the manuscript. Here, the manuscript on the right is very difficult to read. It was a seminar in Bogota led by Fernando that for a whole semester really plunged into reading this in many ways in the modern readings. But in a way, this is a very strong claim, because after a century and a half of different takes on these and different re-explanations and the role of linear algebra, that of course wasn't there back then, he said, well, when you do it with model theory, it is Galois. It is not Galois plus linear algebra plus acting plus net, but no, it is Galois. And that's very interesting, because it is at the same time much more general and at the same time much more similar to what was there 200 years ago. So in what sense? And with which abstractions? Because there are some abstractions that we'll see, and that where Grothendieck's early ideas will enter, as I said, as an issue. He never really, it was kind of cast him aside. So Medvedev and Villaveces have an invitation to model theoretic Galois theory from 2010 that I think is a wonderful little introduction where they draw the parallel. On the right-hand side, you have classical Galois theory. ACF, algebraically closed fields, complex numbers, is the big model for a while. I'm speaking about really classical Galois theory here. And you're looking at fields inside the complex numbers. On the left-hand side, you have a theory, first order theory for now, and you have some model of the theory that is sufficiently saturated, like the complex numbers are for ACF. And you're looking at submodels of that big model N. Now, so this thing in the top is just from before. You have notions, and I'll give very quickly a description of this, but let us just ponder the parallel you have. You have the degree of an extension, you have the role of the automorphism group, you have that both left and right, and there is a notion of normality of an extension and of a splitting extension for model theory. That's one of the things that are possible because of Scheler's imaginaries, but that were made visible by Poisson and are explained in a nice way in this paper by Medvedev and Takubagashi that I mentioned. And then we go on. So you recover the Galois correspondence on the left and on the right, and you see a lot of parallel. Everything works fine. But of course, I have here a lot of things on the right here. There is a question, well, there are some differences that are lost in that translation, as always. What is lost? For instance, the language might not have function symbols. Then, and of course, ACF is made with function symbols. Of course, it's algebraic. Polynomials, well, they're no longer polynomials. They have to be replaced by formulas. If you have something called quantifier elimination, your formulas will resemble polynomials. But in general, they may be quite more complicated. Or, well, you have the notion of extension, B extends A. It may be very far from linear over A. And linear over A is something that plays an important role in the development of the details of the Galois theory. Or the degree of an extension might not be given by vector space dimension. So it may be a more complicated notion of dimension than vector space dimension that works so nicely for classical Galois theory and even some of the extensions. And of course, you won't find any norms, traces, determinants, and that sort of thing. That's kind of to be expected. But anyway, okay. I have here, I would prefer to leave some time for discussion. I have here 3 slides or 4 with definitions, but there is one point that I want to single out because that point is important for what we need for stability. So let me just go on a little bit. You have some model of T that is sufficiently saturated. That is like the complex numbers in the classical case. You have a formula that's like your polynomial, except can be much more complicated. And you have a notion of a solution that is just an element that in the model satisfies the formula. That so far is quite parallel. There are notions of algebraic closure in model theory and even tighter definable closure. So something is definable if you can find a definition. You can write a formula whose only solution is what you want to define. That's one solution. But it may happen that something has that formula, but the definition works with an orbit of other elements that are defined. If that orbit is finite, then we call B algebraic, just as you would call it algebraic in the ACF case. Now, if that orbit of B over A is finite, we call the degree of B over A that cardinality, and you have a finite number. This cardinality is the degree. So here, the parallel kind of works quite nicely. So you have a notion of a finite extension. B is finite, extension of A, if there is some tuple B of the intersection with the algebraic closure, such that B is included in the definable closure of the union. So it gets slightly more technical, but this is something that if you're familiar with classical Galois theory, will be like a translation. If not, then I just tell you that you have a notion that is crucial in the work of Galois, in the later works in Galois theory, and it reappears here, normality. So B is normal over A if the orbit of C for every element of C is contained in B. That we may just take as a definition for now, but this captures normality in the correct way in model theory. And then splitting maybe is perhaps the most the slightly most technical definition. B is splitting over I didn't define the irreducible polynomial or formula that also exists here over A if the orbit is contained. But let's jump over the first half if we want. There is a definition of being splitting, but what's important here is perhaps that we have a notion of finite extensions that works, and we also have multiplicity of the degree that I had defined. One can recover these things. So one could wonder what's lost and why is this an issue after all? Well, in Galois theory, of course, at some point, in classical Galois theory, at some point, you need something like symmetric polynomials. You need something like you fix something small that somehow controls orbits that are outside. And that role of permutations, fixing something small that somehow control orbits that are outside is a key point that Galois himself had recognized, and that in a way is what reappears here with the role of what happens to imaginaries. So this notion that appears here in green, the word definably, closed intermediate extension, becomes the key role. We don't want to just classify models, we want to classify more sets or put more sets into a Galois correspondence. And this issue of definability and how an orbit may or may not be controlled by something small, that becomes quite an issue. Or to put it in another way, there is this definition that the theory codifies finite sets of tuples. So algebraically closed fields, of course, codify finite sets of tuples through symmetric polynomials. But here is a technical definition, the more general definition, but it is a definition that anyone can recognize from Galois theory. For every natural number, for every finite set, there is some B that is fixed by all automorphisms of that big model, if and only if the finite set is fixed as a set. This is the role of symmetric polynomials, and it is key, and this is something that may or may not happen in model theory. It depends on the theory. Now, there are additional technical steps that are in this quasi reading of Scheller. By the way, he mentions Marc Krasner, another French mathematician, as the source of his own, of Quasar's own inspiration in this reading of Scheller. And here, of course, is the source, major source of so many ideas. That's the first big work of Scheller. So anyway, what I want to say is that an additional technicality that I completely skipped over is you have to be able to do amalgamation in a good way of small sets or small extensions, and the possibility of controlling these amalgamations in a meaningful way. That's the core of what comes next. That's the core of stability theory. It is, in a way, a theory of controlling amalgamations and extensions. When you have extensions of some modes of some theory, you may want to be able to control them, and sometimes it's possible, sometimes it is not possible to control them. So think of it a little bit this way. You have some type or some orbit bringing some interactions here, and you put them in a variable x, and you have some second orbit bringing some other interactions, some variable y. Well, you have the two situations. Maybe x and y, the new interactions can be separated into properties of x and properties of y and nothing else. Or maybe you do get new properties of x and y that cannot be reduced. Now, that's sort of a way of speaking. It's very loose and very general, but it is at the heart of some of the possibility of doing classification theory. Let me just stop here, this part of this really, very brief and vague description of the Galois theory, a la Krasner, a la Quasar, based on Scheller. And let us say something important here and then go to stability. So the key hypothesis to the early possibility of defining a good Galois group of theory was stability. Roughly, a solid theory of definability of orbits. So orbits are controlled. They have this sort of definability. You can control this finite set that were appearing before. We call them Galois types or types. We call them Galois types these days in generalizations of stability to non-first order situations that we call abstract elementary classes. I will say a little bit of that at the end, in honor to Galois, of course. And the action of the automorphism group of a large structure. So we now take Detuve. So there is this early link with Grothendieck that is quite interesting. Let me just speak a little bit about the context for classification theory. So forget about all that I was saying before. Now consider this formless magma, or shapeless magma of all possible mathematical structure. Is it like some kind of random noise? Like some people would claim that yes, it is indeed some kind of random noise, and the patterns appear because of some kind of external. There are people who believe that, but perhaps not quite. Our own experience is quite different from that. Groups fields, direct varieties, or Sobolev spaces, or inner modes of set theory, or function spaces, or whatever. There are structures that are kind of more important to every one of us, and not for completely singularity reasons. They're more important to whole groups of people or whole mathematical cultures. So is this a homogeneous world, or what kind of classification is there? So model theory has a quite strong classification of all first-order theories. It's now being extended by, originally by Scheller, and now by some other people, including ourselves in our group in Bogota. It's been extended, this classification. So you have here some familiar structures. These are familiar, very classical structures. I won't go over the name. You can add, of course, this is a much longer list, and you can add lots of structures that you consider should be there and that have appeared here and that appear kind of everywhere in mathematics. Elliptic curves, for instance. And then words like dimension, rank, degree, density character, if you're doing like Banach spaces, seem to appear attached to these structures and control them and allow us to capture them. So one goes first from arbitrary structures, then there is some kind of hierarchy of types of structures that's given by stability theory. There is a kind of best depending to who is judging this, but there is kind of a good part of the hierarchy that's and then there is a part that goes beyond direct control by a logic. Now let me just single out something that has happened. So there is what emerges from that theory, from the yellow book I mentioned before, after a while, is quite deep taxonomy of classes of structures, dividing lines of classes of structures, many dividing lines. The red one here is stable on the one hand. So what's a dividing line? And that's an interesting philosophical concept. The two sides have an interesting meaning. If you're on the left-hand side, you're stable, and stable will mean good for Galois theory. Just take that definition here, in the sense that the amalgams are controlled. There is also Galois theory for the other ones, now by Khrushchevsky, that's a different story. But if you're not stable, you have an order, an infinite order inside. And that's also a very meaningful mathematical situation, having a copy of like rationals or the integers or whatever. But there are many other dividing lines. That was Schellack's plan of bringing dividing lines. I mentioned here some of the famous ones, but maybe the first line is what's important for us. That's the main dividing line, because that's the one that is more connected to the first part of that possibility of doing Galois theory. And we end up with some sort of map of first-order theories where you have very different zones. Here, algebraically closed fields, characteristic P, for instance, and that's where Galois theory started. And then, kind of farther away, ZFC, piano arithmetic at the other end, and in between structures that are important. But for instance, the reals have an order, and then they cannot be stable in this kind of area. Galois theory. Stability theory is a way of not only mapping out this, but also finding general similarities and maybe extending techniques that work very nicely in one area to some area, perhaps at the price of having to give up some of the good properties, but generalizing in a meaningful way. If you want, on this website, rapprochement.dividing.com, there is even an interactive version of this same map. So I see that if you click on stable on the right-hand side, then in pink, you have here the stable zone. But then you see here, you have like 40 different zones at this point, and he gives you examples in mathematics. It's each one of these red dots here is a mathematical theory, well-known mathematical theory, or somehow well-known mathematical theory, like algebraically closed fields. Here will be at that upper corner of the lower corner in the strongly minimal area. And you can also, it is a very useful tool online that you can use. You can check it if you want, like a real comment. And was this big aim in model theory that was triggered by stability of getting a sort of a asymptotic behavior for all theories that is called the main gap. But let us focus on stability. First, before going to the end, that definition of stability theory has very interesting spin-offs. like Khrushchevsky's proof of the Mordell line conjecture. It is also connected to the work of some people here. The model-theoretic analysis of the André-Oort conjecture, quite recently approved by Casal, Freitag, and Lagoon, the conjecture by Van André from around 1895, using the model theory of the potentially closed fields, model-theoretic analysis of analytic functions, and Grothendieck standard conjecture that very much brought by the Zilber School in Oxford. And there are many other things. The original, the first, the most important dividing line was stability for the whole subject. Then you have all the additional dividing lines. So let us say what this is. But let us go to Grothendieck. In 1952, and this is explained by Itai Ben-Yaakov in a note, the fundamental theorem of stability, which is the equivalence between not having an order, so being on the first map I drew, it was the left-hand side, and the definability of types that I said would be important for Galois theory. Well, according to Itai, and this is a very short note that one can read. So in his work in Banach space theory and in Hilbert spaces, Grothendieck had this notion: given a topological space X and a dense subset X0, then the following are equivalent. For A, the Banach space of bounded complex values functions on X equipped with the supreme norm. So these are equivalent. A is relatively weakly compact in CBX, and A is bounded. And for all sequences at N from that collection of functions and Xn points, you can exchange the order in which you take the limits. So the limit N, limit M is equal to the limit M and the limit over N when both limits exist. Now, why let me bring this up? Of course, the details of how this gives or how this implies, there is a way to extract from this the first theorem of stability theory, the very beginning of stability theory, as I was describing it before, after. There is an interesting situation. This is 1952. Stability theory, the book by Scheller is from 1978, 80. But the development of stability theory is really from the early 70s, from Scheller's thesis, and it comes from Morley's work in stability theory. It was about classifying theories, about looking for spectra, but there was an equivalence between the possibility of defining an order and the possibility of and the definability of the type. Now, in a way, the way we read in model theory this exchangeability of the two limits is the order cannot be, there is no way to capture a linear order on the types, and there is a specific, clean way of doing the translation. That means you cannot define an order, an infinite order in the theory. So this is specific for Banach space theory, but Ben-Yaakov shows how this actually implies this for all first-order theories. That's a very nice remark, I think. And now the other property, I'm certainly not an expert here, and there are experts here who can see why being relatively weakly compact in CBX is a form of good definability. I won't go into that, but you see here, on the one hand, you have some kind of a very good behavior in terms of controlling, orbits. And there is some kind of a periodicity of the orbits, and then the exchangeability of the limits. Krivine had already used later, without acknowledging Grothendieck, that there was a kind of early use, but Krivine was also a logician working in Banach space theory, and he kind of had an early, and then Scheller made this explode really for arbitrary theories, and now for many concepts, many situations outside of first order theories. Okay, let me jump a little bit of let me give you this, because there is a translation that is kind of more category theoretical, where one, so this is kind of going back to Galois theory, but making the connection with stability theory. You have this category really fleshed out by Mackay and Regis that really consists of the definable sets of the theory. So you have a theory, first order theory, some vocabulary, and then you take the category of all the definable sets of the theory. So objects are equivalence classes between L formulas, really. And morphisms correspond to definable functions. Now, the solution set is what you call the defined set. So it was the solution set we had before. But then in this way, really models of the theory are functors from that original category to the category of all sets. And it turns out that natural transformations correspond to what we call in model theory elementary maps. So this category is Boolean, it is extensive, so in a way, this gives this correspondence. Now let me give you one more definition here. An interpretation, and I think why do we bring up interpretation here? Because you can recover the notion of stability also through interpretation. And interpretation is perhaps, well, some people have said, Scanlon sees this as the main purpose of model theory in the end. It is such a central purpose that we never mention it normally because it's kind of implicit and but it is at the heart of many things. So an interpretation between a theory T0 and T, and you will see why T0 and T, is some Boolean and extensive morphism, iota, going from T0, from that category of definable sets in the first theory to the corresponding category for the second theory. So being Boolean and extensively preserves finite limits, induces homomorphisms, and so on between the categories. But it is just some functor, so it is a translation between the two theories. But this becomes interesting when we lift it to classes of models. So giving one such interpretation, iota from T0 into T, one can do iota star from the models of T, so it goes backward to the models of T0, essentially by computing this way, M0. So a model of T, remember, was a functor that was selecting, so the functor was selecting for each definable set given in the category T, it was selecting some set. And then all of that was put together into a model. The model was the coherent way of doing that. Then well, all you do is you compose with the interpretation and you get a model of the theory T0. So here it is T0, sorry. Yeah, here it is T0 because iota was going from T0 into T. So here it is from T0 into set. And you get a model of T0. And then this also works well for elementary embeddings. Why do I bring this up? Because, an example of this, of course, but we all know it from a long time ago, from the definables of algebraically closed fields into the definables of real closed fields. So we have the two theories. When iota of a field is r squared here, for if R is a model of RCF, so it goes this way. You have a real closed field, so you have like the reals, R is like the reals, then this corresponds to our interpretation of the complex numbers over the reals, as we have known for roughly 200 and something years, I guess. And the iota star of this is exactly the construction that we are so familiar with, the complex numbers. But there are many other natural examples of this interpretation, like retracts or Boolean algebras in Boolean rings, and so on. Stability comes back here. It is reflected in a natural way in interpretations. An interpretation is stable if, for each model, the expanded interpretation is an inversion. But this means really that each definable in the iota of x, for x of the T0 that is being interpreted in, using parameters from M, is the image of a definable set using parameters from M0. So you see, what maybe emerges here is, in a way, stability is also quite naturally corresponds to interpretation and definability of the interpretation. And this was remarked by Kamensky, a former student of Khrushchevsky, who's in Beersheba, in Israel. He went as far as reframing the whole Galois theory of model theory, following directly SGA 1. So it is kind of a more faithful to Grothendieck way of reconstructing the Galois theory. It is not completely new compared to the quasar reconstruction that I described before, but the word stability comes into the picture also here. So we have this Galois group theory, the automorphism group and this works well when the theory is a stable theory, when it is in that part of the theories that was stable. Okay, so now I think I go to the last part of this. So I call this three now ascents after I have described in more detail the way Galois theory, ball theory is built a la Poisson. I have kind of mentioned there is also a way of building it more a la Grothendieck in some sense, but you have several restrictions there. First of all, it has to be so far, what I described, a first order theory. And there is a technicality, that is the very strong technicality, that the theory, in order to have push the Galois theory forward well, needs to be a stable theory. So the keyword is, the second keyword is stability, and the first keyword that was here was first order theories. And one might ask, well, first of all, to what degree is this really first order theoretical phenomenon? To what degree is Galois theory, the Galois theory of model theory, something really linked to model theory? One could say, well, maybe it is very first order, maybe because definability comes into the picture so much, and the extension of the phenomenon of what we call canonical basis in model theory, that comes from symmetric polynomials, seems to be linked to the formulas you have. So you seem to depend maybe on a category that works very close to these categories attached to first order, to models of first order theory, or maybe there is something a little bit more general going on there. I claim the second line is what happens. It is a more general phenomenon, but it is a more general phenomenon that one has to take with a lot of it has to be done in an extremely careful way, because definability has to come into the picture. Definability for us logicians is not restricted to first order. Of course, there is infinitary logic definability. There are many other ways of tracking definability. Even for Banach spaces, it is not quite first order. The logic for Banach spaces is continuous model theory, so the notion of definability is somehow more general already. So the first question is, to what degree does this depend on a specific definability context? Now, the second one is, and what can one do when even in first order, somehow the orbits that are so central to any constructor, so the action of the automorphism group and then its quotients and so on, you want to control. If the orbits don't have good definability features of the orbits themselves, then, well, the translation, the early translation, the Poisson translation, or even the Kamiensky-Khrushchevsky translations, they don't quite work so well. They fail once one steps out of stable theories. But then if you want to do Galois theory for p-adic in this or even for real closed fields, or even for expansions with automorphisms that are generic, that may fall out of stability. So there are many situations that are stable, that are very interesting, but there are many situations that are not stable. So that's the second obstruction that is not kind of now being addressed. The second obstruction is being addressed by Khrushchevsky. The first obstruction is being addressed by, well, we're trying several different things that before we have to kind of get a better grip on definability of what we call abstract elementary classes, and that's more the work of different people, some more theorists. There is a third line that I want just to mention, just because higher categories have been so much mentioned here and discussed here, and there is a kind of a development of higher stability that may make sense to some people here. So this last part will be kind of a very rough description of three lines that are happening at the moment. The first one then was that it's obstruction, but what happens when the theory is not stable but still first order? So Krzyzewski started quite recently, around 2019, to work on definability patterns. He called them that way. He calls them that way for first order theories or slightly more general contexts, which are about finding the right structure supporting, so the right object of which you would take the automorphism group, allowing a robust correspondence for arbitrary first order T. So this was the automorphism group of that big model that I gave, but for stability. He of course expands. Well, he does it expanding on the class on the first version we saw, the Poisson version of Galois theory, not on the Kamensky, his student himself, but on the Poisson. But that's one possibility. What he does, and this is a very rough description, uses a language he calls a pattern language adapted to build theories of type spaces or orbit spaces. They are spaces, they have their topology, and building a theory with predicates capturing how definable or how far from definable is a given tuple of types or orbits by a given formula, and then finding models for this theory and proving their canonicity. So he calls that the core, and he proves it is canonical, and he proves it gives you the right object to get the Galois correspondence. And then he goes in many directions from there. Let me just say something very brief. You're linking orbits. So these Pn, P1, Pn here are orbits. And all of this is kind of a linking. What def here is kind of a predicate. You add a predicate that somehow captures what would be a kind of a definition scheme if there was. Allow me just to say that in the stable case, all of this trivializes. All of this is already there. And now we kind of expand the language and have to look at the topology of the orbits themselves. Okay. Now, forget about the details of this. This is just a line that is happening now that I think is interesting. There is another line that I want to maybe describe quickly here. Vazet in 2016 introduced what he called Galois modelizations for abstract elementary classes. Abstract elementary classes are just more theoretical situations where instead of giving yourself an a priori logic, you do have a vocabulary, but you give yourself enough closure notions, and that has been successful at building stability theory the way we built it before. Only very recently, only in the past 3 years, 2 years, we have been able to come up with good axiomatizations of given an abstract elementary class. There is a sentence that axiomatizes it, my joint work with Scheller, and this is kind of being improved at the moment. So there is a kind of a more syntactic approach that would be necessary for that line. So these are Krzyzewski's abstract cores, but I think they have kind of very cheap flavor we may discuss at some point. But let me close. I think this is a good time to finish. Have some time for maybe questions or something. In their current work, Chernikov at UCLA and Tausner in Pennsylvania, they have embarked in another theory that I think would be dear to Grothendieck's ideas in some way, which is higher stability. Because stability, and remember, may be recast as a question of recovering information about binary relations given with some obstruction. So in the case of stability, because of the fundamental theorem I mentioned, the obstruction is order, infinite order. So your relation does not define an infinite order, but you might have another obstruction. It doesn't define some infinite tree, for instance. It usually comes in the form of, it doesn't define some combinatorial object, order, binary tree, some kind of more complicated tree, and so on. So there's some kind of forbidden situation here in your binary relation. Now, there is a question, when can you record your binary relation that is linking X and Y in terms of some unary relation about X and some unary relation about Y? Several classical dividing lines have formative R, X, Y satisfies the obstruction, then it may be approximated. Of course, the approximated here may be very long, many pages long in the details, by unary relations. Many of the theorems of classical stability theory, one learns in the course of stability theory, are a way of fleshing out what is here said in 2 lines. It's really many theorems that, decomposability theorems, all sorts of, but in a way, it's about the interaction between binary relations and their approximability by unary relations. And we have seen, at least I hope I managed to convey here, how that 2 and 1, that interplay between 2 and 1 has been productive and is still being productive for so many different things in stability theory. The spin-off of stability theory has been linked to number theory, to the Mordell-Lamp conjecture, Truszowski's work in the 1990s, and it is being connected to in different ways into Annabellian geometry that I know no details about, that I know it exists, but you know here. And but Chernikov and Tausner, they take this line, well, why not try to think about ternary relations and their obstruction by, their approximability by binary relations. And they try, and they do, it exists already. In some cases, it already exists. Some people, oh, it already existed. It was part of some definition, or it was implied by the 2, or in some cases, for some of the dividing lines, it happens already. But for stability itself, apparently it doesn't. So stability, the first dividing line, the one that was, visualized for Banach spaces by Grothendieck 70 years ago already. It doesn't really, that one line doesn't really have an n-dimensional situation. It is quite complicated in Chernikov and Tausner. I was speaking to Achim, who's at UCLA, but came on the first day here about this project, and at the moment it is still very messy. It needs a lot of work. This is deeply related to much earlier work originally due to Scheller from, it was called excellent classes. They had a major impact on the development of the deepest theorems of classification theory, sort of the main gap I mentioned, how you analyze models of arbitrary cardinality into countable models. Well, you need to take into account dimensional interactions happening at the models of size Aleph n, at the Aleph n's. And those dimensional interactions have a flavor of higher stability, but for some specific situations. And also understanding phenomena in infinitary logic, L omega 1 omega, and various other non-elementary contexts. But I close here. Thank you all for your attention with this quote. Oh, I should have this in French, and it is in French. So this is my translation to English. If the Greeks were so attached to geometry, wasn't it that they thought by tracing lines with no words? However, or maybe just because of that, they produced a perfect axiomatic. Euclid's postulates construction, limiting what one is allowed to trace. In the Galois-3 maximum data. Thank you very much.